Hello everyone, and welcome back to a new video in programming the finite element method using MATLAB. In this video we are going to continue our efforts, and this time we are in the undo static condensation. The undo static condensation is basically the antidote or the inverse of what we did when we applied the boundary conditions. So we are going to take the F1, F2 and K1 and so on and glue them back to get the forces and get the displacements. So, of course, before I start, I want to mention that this is part of two video series talking about the finite element method in the theory and programming. Both of them are linked at the top right. And of course, our dear channel members have access to the entire source code. However, if you're not a channel member, then don't worry, because every single line of code is going to be written in front of you, and you can write along and you would have the exact same code as mine. So with that being said, and without further ado, sit back, relax, and enjoy the show. Okay, now we're gonna undo our static condensation. So we are here. I'm gonna go down to its application, which is here. Let me close the solve and open the undo, and let's start programming. Now, I highly recommend that you double check the apply boundary condition video if you forget what we have done, because now I will keep my commentary to a minimum because it's a repetition of what we have done in the apply boundary conditions. I need to keep tabs of the rows of the D1s and D2s. This is something I need to do. And then I will basically start our work. So here I would say number of load cases. This is going to equal the length of object, which is the controller, str load cases, and that's the number of the load cases. Now here I need to go through every single one of the degrees of freedom. Now, I don't need the number of nodes. There is an easy way of doing things since I have the stiffness matrix, as I suppose is another style of doing things. I will go with a for loop, and here I will go for I equals from 1 to the size of the, it's kind of fancier, object.stiff global stiffness matrix, and I'm going to take the number of rows, which is the number of degrees of freedom I have. It's kind of fancy schmancy. You could go for the total nodes and degrees of freedom. I kind of want to show off, so I'm going to use global stiffness matrix because the worst has been done and now we can enjoy ourselves. By worst, I mean the loads. So here, once again, we're going to go through every single degree of freedom and we're going to ask the question, if is none the object.boundary condition, so we have a boundary condition, otherwise we don't have. So if it is a boundary condition, then let me put a comment here. If it is a NaN, which means it is a boundary condition, stuff will happen. So here I will say the degree of freedom is a boundary condition. So what will happen? If that's a boundary condition, then we need to store the stuff in D1 into the global displacement matrix. So here I will say object global displacement matrix of, now of course I have multiple load cases, so I think I should need a loop for the load cases. So let me loop through the load cases. I'll go here and say for j equals from 1 to the length of the object.str load cases. So we are looping through the load cases, and now we're going to store the stuff. So here object.global displacement matrix of degree of freedom I and load case j, this equals object dot. Now I'm gonna take from D1 because we are in a non-boundary condition. So this is not a boundary condition. So I'm gonna take from D1 here. When I take from D1, I'm gonna take from D1 at row D1 and column load case. I just realized I made the typical mistake. First of all, I could go here. And second of all, the typical mistake is that MATLAB starts indexing at 1, not at 0. So I corrected the typical mistake, and now we continue. Also, since it is not a boundary condition, then object.global load matrix of I and j, this is going to equal the object.f1 at the row f1 and the load case j. Now, since I added something, I need to increment, of course, the rows and the columns. So row f1 equals row f1 plus 1, and row d1 equals row d1 plus 1. For more details, check out the previous video of the apply boundary condition. Now here, the degree of freedom is a boundary condition. So now we are gonna cycle through all the load cases, and we're gonna store from D2 and F2 rather than D1 and F1 because we are in a boundary condition domain. So this is D2, that is F2, and here I have row F2 equals row F2 plus 1, and row D2 equals row D2 plus 1. I think that's that. Yeah, that's how we undo the static condensation. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a static condensation sized shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel. I will catch you in the next video. Bye bye.